did in class, particularly this second example, we ran sort of out of time, and some of the values were rushed. And the last thing I want to do is rush through some of these calculations. They're really simple, but I really want to take my time with them. So what we're going to do is we're going to take each of these one at a time. I'll just go ahead and work in order and do the shear one first. So first off, let's talk about the shape. Again, what we're doing is we're installing a shear release here at C, and then we're displacing that structure such that we move the left side down and the right side up. Remember, we're keeping the structure fixed at the supports because again, if you take a load and you put it directly over the support, you're not going to generate any internal response in the beam. So the left side goes down, the right side goes up. And then the last thing to keep in mind beyond anchoring the supports is look at the beam once the release has been placed and ask yourself how many rigid segments are left in the beam. And that'll be 3 because we have this piece of the beam. That's one rigid piece. This is one rigid piece right here. That's all one rigid link of the beam. And then finally we have this right here. So if there's 3 rigid links, there's going to be 3 elements to the influence line. Just because we have the beam and the elements fixed there at the supports doesn't mean that the influence line changes direction at the supports. It remains fixed there. So that's why we go down on the left, up on the right, but this middle segment, it's going to go through there. It's going to go like this. Right side's going to go up. And then that hinge is going to serve to change the direction. And hence, that's why we get the influence line that you can see here. That one's drawn a lot neater than I would draw it by hand. Okay, now let's look at some of the values. So how do we do that? Well, ultimately what we're trying to determine is this height here, which we'll call H1, and this height here, which we'll call H2. We're going to determine these heights based on 2 key pieces of information. One, that the total height is 1, and the second is that the slope of these 2 lines, particularly this one and this one, are identical. In other words, when you install a shear release, you move the beam through a shear displacement. You release the beam's ability to resist shear, but not the beam's ability to resist moment. So those 2 lines are at the same slope. So how would we determine the slope of the line on the left? Well, it would be H1 over the length, which would be 14. So I'm talking about this diagonal line that you see right there. That's H1, and then that's 14 feet. I'm just using basically that sort of triangle right there in order to determine that slope ratio. Likewise, over here, I'm using H2 over 6. So the second fact I'm going to use is that H1 is to 14 as H2 is to 6. So let's look at that and let's see if we can solve for some of these values. I'm going to clear off these here because it's going to get a little crowded, and I want to try and keep the calculations as neat as possible. So if I look at this expression here, I can solve for H2, for instance, as 6 over 14 H1. So I'm just multiplying both sides of the equation by 6. Or H2 is 3/7 H1. Okay. So if I have H1 plus H2 is 1.0, and I have H1 plus 3/7 H1 is 10, or sorry, 10, that's not 10, that's 1, why did I say 10? H1 plus 3/7 H1 is 1. Well, I know why I said 10, because this is H1 times 1 plus 3/7, right? Because that's multiplied by 1, that's multiplied by 3/7, so I'm just factoring. And so H1 is multiplied by 10/7, right? Because 1 plus 3/7 is 7/7 plus 3/7, that's just 10 over 7. And so therefore H1 is 7 over 10, just flip and multiply. And if h1 is 7 over 10, then h2 has to be 3 over 10, right? Because the total jump, the total change in displacement has to be 1. So that makes this value here 0.7, or more specifically negative 0.7, because it's a change in, or because the height's negative, it's going down. And this is positive 0.3. And so that takes care of the values there. And so really the only other key value that we need to figure out is what's going on right there. That's the only one that's a little unique. And so the way I'm going to do that is I'm going to look specifically at this triangle right there. I'm sort of filling it in, and this triangle. And the reason why is because both of those diagonal lines are at the same slope. And so if I look at the triangle on the right and I look at that slope ratio, if I look at this one right here, that slope is going to be 0.7 is to 14, because I'm getting that 14 from right here. This one is going to be, maybe we'll call this, I don't want to use the term H. I don't know, maybe we'll call it X. That slope ratio over here is going to be the rise x over 8, whatever that slope, whatever that height is. We got to figure that out. So 0.7 is to 14 as some value is to 8. I don't know what that value is, but I can solve for that as 0.7 times 8 over 14. And when you solve that out, you'll get 0.4. So that makes this 0.4, and that is your influence line. Here, I'll clean this up a little bit. Again, I don't want it to get too crowded. And that's the influence line. That is the influence line for the shear at section 1-1. And so again, what those values represent are the internal shears right there as you move the load across the structure. Similarly, with the moment, we do the same thing with the moment, although instead of installing a shear release, we install a moment release. So we're installing a hinge right here at section 1-1, and then we're moving that through a unit displacement, but with moments, we're doing it through a unit rotation. And so what that means is, I'm going to take this section, rotate it up, and take this section and sort of rotate it like that. Whatever this slope is plus whatever this slope is, those two slopes have to sum up to be 1. Now, as for the rest of the influence line, the way that we construct that, well, once we install that hinge, you have to ask how many rigid segments, how many rigid links are there in the beam? And there's 3, right? Because you've got, this segment, that's a solid piece of the beam until we get to that hinge. And then we have another solid piece of the beam. That's all one solid piece of the beam. And then we get to this solid piece of the beam. So there's 3 different rigid links. And so those 3 rigid links are all going to move together. We anchor it at the supports, anchor it at the supports, because 0 at the supports. And so if you lift this point or this hinge at section 1-1 up, what's it going to do? It's going to, sort of go like that. And so that's what you can see here. That's what I have down here. That's the influence line for the moment at section 1-1. The only thing left to do is to go through and compute the values. And so I'll scroll down a little bit and give myself a little room on that. So first thing we need to do is pay attention to this point right here. We want to find out that height, right? Now, just so we remember from up top, that is 14 feet right here, and this is 6 feet right here. And so the way that we'll do that, let me, give me a second. Oh, come on. Okay, so we will strike a line just so we can split up the calculations here. We need to determine that height, and so we're going to do that by looking at the slopes on either end. So the slope on the left is h over 14, plus the slope on the right is h over 6. And that total slope needs to equal 1. And at this point, it just becomes, a basic arithmetic or an algebra problem. what I'll do is I'll say 6 times h over 6 times 14 plus 14 times h over 6 times 14 equals 1. So I'm doing that so that I have a common denominator. So we'll have 6h plus 14h all over 6 times 14 equals 1. And so from there, what do? We've got, here, I'll move that up here. So we have 20h over 6 times 14 is 84 is 1. So h is 84 over 20, which is 4.2. So what that means is this value right there, oh, I want that in blue. That value right there is 4.2. And so we've got pretty much, again, it's a similar instance. We've got every value figured out on the influence line but that one, and maybe we'll call that x. And I'm going to use a similar observation. This diagonal path in the center of the beam, that's all one similar slope. And so I can look at each of those, similar triangles and say, okay, what's going on with that triangle? What's going on with that triangle? They have to be at the same slip ratio. And so how do I do that? Oh, I'm erasing stuff, erasing more than I would like. Sorry about that. Okay, so what do I have here for this x height? Well, let's see. The slope ratio on this side is 4.2 is to 14, and the slope ratio on this side is whatever that height is to 8. Because remember, from the original beam, you can see up here that distance is 8. So 4.2 is to 14 as x is to 8. So x is 4.2 times 8 over 14. We actually kind of used a very similar expression before. We just had a different, instead of 4.2, we had 0.7. So 4.2 times 8 over 14 is 2.4. And so that makes this, I'll erase that out. That's going to be negative 2.4 because it's on the negative side of the axis. And so just clean my drawings up a little bit. So, I keep erasing those guidelines. I don't want to. Maybe I'll use my little lasso tool. Hold on. All right. And there we go. So if I scroll up a little bit just to summarize, these are the influence lines for the shear and moment at the section of interest. We can use similar observations for the last problem. I think I went through that one a little bit better just with timing and whatnot. So hopefully this is fairly clear, and this clarifies some of the math that was done in order to get those intermediate values. And on Friday, what we'll do is we'll look at cantilevered segments and trusses. That's all I have. We'll see you all then.